Hi guys, today I'm going to work through the worked examples from exercise 4.2 of your jacplus Year 12 textbook. So we're talking about log laws and equations here. So something we want to think about before we start is that logs and exponentials are the opposite. So they're inverse functions. So when we have indices and you have, for example, m cubed times m squared, well, you would say m to the power of 3 plus 2. So when we multiply indices, we actually add the powers. So for logs, if we are going to add logs, so if we have log 3, 5 plus log 3, 7, well then in order to simplify that, we'd say log 3, 5 times 7 is 35. So as long as we've got the same base, we do the opposite to what we do as if there were indices. So look, the first one here involves that, and we've got some addition and subtraction of the logs. So I'm starting with this. So all the bases are the same. We must make sure of that first. They're all base 4. So we can say log 4 64 times 16. And then, well, it's going to be minus log 4 256. So that's log 4 64 times 16 divided by 256. So the same thing, if you are dividing indices, then you would subtract the powers. But for logs, when we subtract logs, we divide. Now, these numbers are quite large, so I'm thinking there's probably a better way that we can do this. And I think what I might do is change that 64, 16 and 256 into something with a base of 4. So let's see what we can do. So we could keep going like this. It's not wrong. It's just that if it's not, with CAS, it's quite yuck to work with such large numbers there. So let's see. I'm going to change it to log 4, 4 to the power of 3 is 64, plus log 4, 4 to the power of 2 is 16, and then minus 256 is 4 to the power of 4, I believe. Yes, log 4, 4 to the power of 4. Okay, so now what we see is we can apply another one of the log laws, and this is that when we have the power, so see we've got 4 to the power of 3, 4 to the power of 2 and 4 to the power of 4, well I'm going to take that power out and put it out the front. So it's a multiplication then. So this turns it into 3 times log 4, 4 plus 2 times log 4, 4 minus 4 times log 4, 4. And now, well, this is going to be a lot easier. Log 4, 4, that equals 1, because remember what log actually refers to. So log 4, 4 means 4 to the power of the answer, which is 1, equals this here. So log 4, 4 is 1, log 3, 3 is 1, log x, x is 1. Anything where you've got the same here and here, it's going to be 1. So 3 times 1 plus 2 times 1 minus 4 times 1. So it's 3 plus 2 minus 4, and it equals 1. So actually we get, we break it down really well there. It ends up something really nice. Notice that we would have got the same thing if we had done it like this. So 64 times 16 divided by 256, well, that must equal 4. So we would get log 4, 4, and that would equal 1. But it's quite a lot of working out there, 64 times 16 and then dividing it by 256. Let's move to part B and 2 log 3, 7. So I'll put it over here. Minus 2 log 3, 21. Okay, so they have the same base, it's log 3. And now in the previous one, we took the power out and put it in front. So, and that was the appropriate thing to do. It was helpful for us. In this case, I think it's going to be helpful for us to take the 2 at the front, well, in both cases, and move that up into the power. So let's see. we get log 3, 7 minus log squared, minus log 3, 21 squared. And, well, 21 squared isn't too nice, so I'm not going to square those just yet. I'm going to make it, well, we've got a minus here, so log 3, subtraction of logs means we divide, so 7 squared over 21 squared. So I think I'm now going to put log 3, 7 over 21, all squared. So I'm just putting that squared there, and I'm actually going to take that out the front now, and I'm going to have 2 times log 3, 7 over 21, that's 1/3. And actually now it's really quite nice. 1/3, well, 3 to the power of -1 is 1 over 3 to the power of 1, which is 1/3. So remember, a negative power will not, something with a negative power will not give a negative answer. It'll mean that it goes into the denominator. So for example, m to the power of -7 is 1 over m to the 7. So in this case here, we've got to solve log 3 1/3. Log 3 1/3, 3 to the power of -1 equals 1/3. So the answer to that is -1. So this here is -1. And -1 times 2 equals -2. So we can get a numerical answer for that one as well. Let's go to the next one. So still part of example 1, we have this. So log 316 and log 364, what some people are going to do, which will be wrong, is try and cancel down at this stage. So some people are going, okay, well, I can divide that by 4, I'll divide that by 4. No, you can't, because it's not 16 and 64, it's log 316 and it's log 364. So it's quite different. So what we can do though, we want to make something common that we can cancel. And I can see that 16 and 64 can both be written with a base of 4. So I could say that equals log 3 4 squared over log 3 4 cubed. And you could, if there's more than one common base, you could use that too. So I mean, you could use 2, and then you would get the same answer if you wanted to use a base 2. I've just chosen 4 because, well, it's quite easy to see it's 4 to the power of 2 and 4 to the power of 3. So now these numbers here, these powers, we can bring them out the front as we've been doing, and that will give us 2 times log 3 4 over 3 times log 3 4. And you don't need these multiplication signs in there. I'm just putting them there to remind you and to really point out that, well, it's a multiplication in the numerator and the denominator. So we can cancel now these, because log 3 4, I don't know what that equals. You could find that out on CAS, but log 3 4, whatever it equals here, is the same thing that it equals in the denominator. So we can cancel it. It's a common factor there. So our answer there would be 2/3. Right, let's see part D. So log 5 of the 4th root of 1 over 625. So this looks pretty ugly, but your best bet would be to put the 4, the 4th root, to be 1 over 625 to the power of 1/4. So I think, dealing with roots and different roots, 5th roots, 4th roots, whatever, it's best to put them as a fractional indice, because then, well, you can get rid of it out the front. So that's 1/4 log 5, 1 over 625. So 625, 5 to the power of 4 would be 625. So 5 to the power of 4 equals 625. That means 5 to the power of -4 equals 1 over 625. Because remember, if it's a negative power, it's 1 over. and then, well, that would be 1 over 625. So in other words, this log 5 of 1 over 625 is -4. And that means we're doing 1/4 times -4. And that equals -1. Okay, so that's the basic log laws. Let's move forward. They're now asking us to solve some equations for x. And here we've got a few little things to look out for. One of which is when we have just a whole number there. And I'll talk about that when we get to example B, but that's quite important. So let's do the first one. This one seems quite okay. So log 464. You might be able to see straight away 4 to the power of x, which is your answer, equals 64. So 4 to the power of whatever equals 64, you can put that there. But the other way you could think about this is, well, you could actually write that out. 4 to the power of x equals 64. And then, well, let's turn this 64 into something with the same base. So as long as it's got the same base, you are able to work with that more easily. So 4 to the power of x equals 4 to the power of 3, because 4 to the power of 3 is 64. We have the same base, so we can cancel them out because there's an equal sign, and that means x equals 3. So pretty straightforward, that one. Let's look at the next one. And this is the one where we have that, that 3 sitting there. So what we want to do with that, we want to turn it into something that has a base 2. So 3 times 1 still equals 3. And we just need to find the form of 1 that allows us to have a base 2. And that is log 2, 2. Because 2 to the power of 1 equals 2. So 3 times log 2, 2 equals 3. 3 times 1 equals 3. So I'm going to change this part B to log 2, 3x plus 3 log 2, 2 equals log 2x minus 2. And now, well, let's put this up into the power. Log 2, 3x plus log 2, 2 cubed equals log 2x minus 2. So log 2, 3x plus log 2, 8 equals log 2x minus 2. And now, well, we can multiply these because, well, we're adding logs. So we multiply it, log 2, 3x times 8 equals log 2x minus 2. And at this stage, we have an equal sign. We have the same base logs here. We've applied the log laws, so we can cancel those logs. And now we can just solve it as usual. So 3x times 8 is 24x equals x minus 2. And then, well, that's going to be minus x on both sides. 23x equals -2. And x equals -2 on 23, which is a little bit of a yuck looking answer, but that's what it is. I would suggest to you not to cancel the logs until you've applied the log laws. So people are going to be tempted to cancel the logs out here. We've got an equal sign, we've got the same base log. But the problem with that is then you are likely to say 3x plus 8. So even if you know the log laws really well, you're likely to accidentally do 3x plus 8 equals x minus 2. So I would absolutely suggest that you apply the log law that we've done here. We're multiplying them because when we add logs, we multiply. And then after we've applied all log laws, then you can cross out the logs as long as there's an equal sign. Let's move to the next one. Here we go. All right, so here we've got one which has something squared, and this is a little bit, kind of looks a little bit weird, but actually if we look, we've got log 2x squared and we've got log 2x and then we've got a constant. So this looks awfully similar to a quadratic, and that's exactly what it is. So this is that thing where we say let z equal log 2x, and therefore z squared equals 3 minus 2 log 2x. And I'm not going to put this into the power. I'm just going to leave it at the front because then I can say, oops, then I can just make it a 2z. So now I've got z squared plus 2z minus 3 equals 0. And of course we can just cross multiply this as per usual. It's a pretty easy one, 3 times neg1. So neg1z plus 3z equals 2z, yes. So in our brackets are z plus 3 and z minus 1 equals 0. Now let's see. We must now solve not for z, but for log 2x, or for x, sorry, not log 2x. So z is log 2x. And log 2x minus 1 equals 0. So we get log 2x equals negative 3 and log 2x equals 1. And 2 to the power of negative 3 equals x. X equals 2 to the neg 3. So x equals 1 over 2 cubed is 8. So that's our first answer. The second answer, 2 to the power of 1 equals x. 2 to the power of 1 is 2. So x equals 2 to the power of 1, x equals 2. Now notice that both these answers are relevant and legitimate. They both work. When you're dealing with logs, sometimes you'll get an answer that doesn't work, and we probably will come across one of those in the examples. So I'll put that out if we get one. All right, let's do the next one. I'm just going to move this over here. Okay, so part D, log e 2x plus log e x plus 2 equals log e 6. So applying the log laws, we've got the same base, so we're adding these logs. Let's multiply them. Log e 2x times x plus 2 equals log e 6. Okay, we've got an equal sign. We've got the same base log, so we can cross out these. And we have 2x squared plus 4x equals 6. And I'm going to subtract the 6 on both sides. And now I can solve. So actually I might divide everything by 2. X squared plus 2x minus 3 equals 0. And again we get the same, 3 times neg 1. So we know that works. We did it in the previous example, exactly the same. X plus 3 and x minus 1 equals 0. So let's see. X plus 3 equals 0, x equals neg 3. And x minus 1 equals 0, well that is x equals 1. And we need to think because not both these answers are necessarily going to be viable. And let's see why. So negative 3. The rule is we can't log a negative and we can't log 0. So the domain of a log graph, which we'll see when we do log graphs, a log graph looks like this. So the domain, or the x values we're allowed to have, are that we have from 0 not inclusive to infinity. So it's only the positive real numbers, so r plus. So in other words, you can't log 0, that doesn't work, and you can't log a negative. So we need to check that our answers are going to work in this equation. So I've got 2x, I've got x plus 2, and I've got 6. So the 6 doesn't matter because we're not subbing an x into it. The first value, let's do 1 because, well, I know that one's going to work. 2 times 1 is 2. So log E2, yes, that's logging a positive. 2 plus 2 is 4. Log E4, yes, that's logging a positive. So we can say this will work. So that is one of our solutions. Negative 3. So 2 times negative 3 is negative 6. Log E negative 6, you can't log a negative. So that means that the negative 3 is not a solution. And it wouldn't matter if this one works. Just say that was x plus 5. Negative 3 plus 5 is positive. So yeah, you can log that. But because you can't do it in one of them, it means the whole thing is not going to work. So we're going to reject that answer of negative 3. And we'll reject it because it's outside the domain. So we're not drawing them yet, but I guess, thinking about, you can't log something that's negative or 0, that's very helpful at this point as well. Let's move on. Okay, so the next one's work example 3 is just doing it on CAS. So really, I mean, this is highly straightforward. Just on your CAS, you have 3 buttons that are relevant for log. One is LN, and that means log E, and one is log, and that's log 10. And then we've got another one which looks something like log, it's got a little thing like that, and that means you can put anything into it, any base. So log 10 and log E are really common, so they've made a specific button so you're able to just press it rather than write it in every time. But if you put log 7.5 in, well, you put the 7 in here and the 5 here, and of course it's using decimal places, so you'll decimalize it and you will round it accordingly. I'm not going to do those because I haven't got my CAS with me, but it's highly straightforward. Let's move on. And look, this is a little bit hard. So look, before I do worked example 3, I might just talk a little bit about the change of base rule. And look, in the jacplus textbook, the program rules they say the change of base. So if we've got log AM, and just say we wanted to change to a base B. So whatever base, it could be base 10, it could be base 4, it could be base 100, it doesn't matter what. But if you're changing to base B, so change to base B, it means, well, we're going to put log BM over log BA, and I'll show you why that works. But I guess the quick and easy way to remember is that the thing you're logging goes in the top, and then the little one, the base, the original base, goes in the bottom. So I guess the more important one, the bigger one, is the M. It's not really more important, but the bigger thing there goes in the top. So the top is more important or bigger, and the bottom has the smaller thing, which is the A there. So look, let's look at why it works. So let's say we want to change to base Z, so I'll do a different one here. Let's say we've got Y equals log 2x, and we want to change to base Z. So there's y equals log 2x, and what we also can deduce from that is that 2 to the power of y equals x. So just, this to the power of this equals this, and really, usually we'd write log 2x in the other examples I've done equals y, so 2 to the power of y equals x. So that's how we get that. Now, what we want to do is we're changing to base Z. So if we're changing to base Z, we take the log Z of both sides. So we do log Z to the power of y equals log ZX. And then, of course, you can take this y out the front. Y log Z2 equals log ZX. And then, now we can divide everything by log 2Z. Log Z2. So I'm dividing by this, log Z2. Probably shouldn't have used a Z and a 2 in the same example. So we get y equals log ZX over log Z2. And what we see, well, there's the x in the top, there's the 2 in the bottom. If we go back to our original, there's the x, there it is in the top, and I might put it in the same colours we had, and there's the 2 in the bottom, there's a little 2 there. So that's how the change of base rule works. You don't need to do that every time, and in fact it's nice if you can remember this, because it's very straightforward. You don't have to go to so much working out. So look, let's now go back to the last example and do that now that we have addressed the change of base. Okay, so if p equals log 5x, and this is actually meant to be log 5x. If you've got the, I'll write it a bit better. P equals log 5x. So if you've got the actual physical textbook, you'll see that it's written like that. It's just a mistake on the website one. So find the following in terms of p. X. Okay, well that's pretty straightforward. Log 5x equals p. So then 5 to the power of p equals x. So that's pretty easy, and look, we no doubt will need that for the next part. So now they want log x 81 in terms of p. Okay, so let's see, log x 81. I'm probably going to make that power 9 to the power of 2 for a start. You don't have to, but I feel like why not make it more simple, because then I mean it's going to be 2 times log x9. So I guess log x9 is a little bit nicer to work with there. Again, you don't have to. I think they do in the textbook. I think they do make it 9 to the power of 2. But look, if they don't, you will end up with the same answer anyway. So let's see, now I can say, well, this is going to be log, 2 times, let's say log 9, 9. So I'm going to make a base of 9 here. So if you had left it as 81, you would be making base 81. And log 9x. So I've taken the big thing here, it goes in the top. The little thing here, whoops. The little thing here, it goes in the bottom. So the same, just using the change of base rule for the same reason as why when we worked it out, when we did all the working out there. So that's going to be, well, log 9 is 1. 2 times 1 over log 9x. Fine, I'm going to put that 2 in the top. 2 over log 9x. And then now I think we can do it. I think we have x, don't we? Yes, x is 5 to the power of p. So 2 over log 9, 5 to the p. So this 5 to the p, that is x because, well, that's what we solved for x in part 1. And I guess that sort of is why they would have wanted you to do that first. It seemed too easy at in the start, but now I can see why they did it. So now, look, I'm going to say 2 over, I'll take that p out the front, so log 9.5, and well, that's it. That's all we can do. So this will be in terms of p. So using the change of base rule, we have just found log x81 in terms of p. And that completes the worked examples from 4.2.